All weather is caused by unequal heating of the Earth's surface. The Earth is a sphere and is heated more at the equator than at the poles. The Earth is also tilted on its axis, which causes seasonal differences in heating at different latitudes. It also rotates on its axis, so that one side heats up during the day while the other side cools at night. Finally, land and water heat and cool at different rates. The curved surface of the Earth causes the sun's rays to strike the equator more directly, resulting in greater heating of the Earth's surface in that region. The following video shows how the tilt of the Earth's axis causes seasonal differences in heating at different latitudes. In the summer, the northern hemisphere is tilted toward the sun, resulting in greater heating as the sun's rays strike the surface more directly. In the winter, the northern hemisphere is tilted away from the sun, which results in less heating of the surface because the sun's rays strike at a more oblique angle.
Why are all the Earth's deserts on a similar latitude? And what gives different parts of the world their climates? What gives us jet streams? And why do we get prevailing winds? It's all to do with the global atmospheric circulation caused by the Earth's rotation. We will look at what this is over a series of short explainer videos. The first step to explain how global circulation patterns affect weather and climate is to understand how temperature varies across the globe. Global circulation is caused by different parts of the world heating up differently. In this first video, we will look at what causes this differential heating. The sun is our main source of heat. This heat travels to us through space in the form of radiation. This radiation is absorbed by clouds, atmospheric gases, and by the Earth's surface. Some parts of the Earth receive more of this radiation than others. The main reason for this is the curvature of the Earth. This curvature means that at higher latitudes, the radiation from the sun is spread over a much larger surface area, while the same amount of energy is much more concentrated near the equator. The radiation also travels through a greater depth of atmosphere nearer the poles in comparison to the equator, so more radiation is lost to scattering and absorption by gases and particles in the atmosphere. The tilt of the Earth also means that polar regions do not see daylight during the winter. Here the Earth is continuously sending out heat to space without any compensating incoming heat from the sun. These cold polar regions are where we see lots of snow and ice. Snow and ice, and also thick cloud, reflect a lot of the sun's radiation back into space. The reflectivity, or albedo, of the underlying surface is an important factor in determining how much of the sun's radiation is used for heating the Earth. The combined effect of all of these processes sets up a thermal gradient between the equator and the poles. In fact, the global radiation balance is such that polewards of 40 degrees latitude, the outgoing heat radiation from the Earth exceeds the incoming heat radiation from the sun. Global circulation acts as a clever air conditioning system, redistributing the heat, stopping the equator becoming hotter and hotter and the poles becoming colder and colder, and these locations becoming uninhabitable. This circulation takes the form of 3 large atmospheric cells, which exist in both northern and southern hemispheres. Our next video shows these cells in more detail. The last video showed that different parts of the Earth heat up differently, with the equator receiving more radiative heat from the sun than the poles. And the purpose of global circulation is to redistribute this heat. If the Earth did not rotate and was a simple landmass with no oceans, we would have a single circulatory cell in each hemisphere, where hotter air would rise at the equator and flow toward the poles. The air would sink as it cools and then return towards the equator. But the unequal distribution of land and ocean and the speed of the Earth's rotation make this circulation system more complicated, giving us a three-cell pattern which exists in both the northern and southern hemispheres. The largest cells are the Hadley cells. At the equator, the warmer, less dense air rises. It rises to a height of about 18 kilometres and spreads out underneath the tropopause. The tropopause acts as a lid to the lowest part of our atmosphere, which contains all of our weather. The warm air spreads out towards the poles, gradually cooling and sinking as it moves, before descending to the surface and flowing back to the equator. The smallest cells are the polar cells. Cold, dense air descending in the polar regions flows at low levels to about 60 to 70 degrees north or south. As the air leaves the polar regions, it starts to warm and rise, returning to the poles at high levels. Between the Hadley and polar cells are the feral cells. Unlike the other cells, the feral cells are not driven by temperature. These cells flow in the opposite direction to the Hadley and polar cells, acting like a gear. These circulating cells not only transport heat from the equator to the poles, but also result in semi-permanent areas of high and low pressure due to the rising and descending parts of the circulation cells, giving us our climatic zones. Where air is rising, an area of low pressure is created, so these areas see much more rainfall. This is why the largest areas of rainforest are found near the equator, and why the United Kingdom has a relatively wet climate. Where air is descending, an area of high pressure forms, giving largely clear skies and little rainfall, which leads to the desert regions. But not all deserts are hot. Antarctica sits under the descending branch of the polar cell and is also classed as a desert. With more precipitation falling in the Sahara, Antarctica is the largest and driest desert overall. Check out our video on atmospheric pressure for more on how pressure leads to weather. Our next video shows how the rotation of the Earth gives us jet streams and prevailing winds. The last video showed that our atmospheric circulation is split into three cells in each hemisphere: the Hadley cell, feral cell, and polar cell. In this third video in the Global Circulation series, we will look at the winds within these cells and how the rotation of the Earth influences these winds to give us jet streams and prevailing wind patterns. As well as being split into three cells, the global circulation pattern is at an angle due to the Earth's rotation. The spin of the Earth induces an apparent motion to the right in the northern hemisphere and to the left in the southern hemisphere. This is the Coriolis effect. The key to the Coriolis effect lies in the fact that the Earth's surface rotates faster at the equator than at the poles. This is because the Earth is wider at the equator, so has further to travel in one day. The result of this means that as air moves away from the equator, it doesn't move in a straight line relative to the Earth's surface. Instead, it appears to an observer on the ground to move in a slightly curved direction. But there is no physical force causing this deflection. As the atmosphere rotates with the Earth, it is just due to the air flowing from a region that is moving faster to a region that is moving more slowly. To explain this further, imagine an air parcel as a ball. The ball is thrown from the equator towards a point near the North Pole. Even though it moves in a straight line, the ball will appear to an observer on the ground to curve away and land to the right of its target, as the point near the North Pole is moving more slowly and is not caught up. If the ball is now thrown from the North Pole towards a point near the equator, it will again appear to a surface observer to land to the right of its target. But this time it's because the Earth's surface at the equator is moving faster and has moved ahead of the ball. This effect only happens on objects that are in motion. This deflection is a major factor in explaining why winds blow anti-clockwise around low pressure and clockwise around high pressure in the northern hemisphere and vice versa in the southern hemisphere. So when flowing towards the North Pole, air is deflected towards the east, and when travelling southwards back towards the equator, it is deflected westwards. The same overall result occurs in the southern hemisphere. How does this lead to eastwards flowing jet streams and prevailing winds? As air moves away from the equator at the top of the Hadley cells towards higher latitudes, it starts to be deflected by the Coriolis force. Just as a skater spins faster by bringing their arms and legs closer to their bodies, air moving away from the equator speeds up as it gets closer to the Earth's spin axis. This process is known as the conservation of angular momentum. The magnitude of the Coriolis force increases towards the poles, so by the time the air reaches 30 to 40 degrees north or south, it is moving in an eastward direction. This subtropical jet stream occurs high in the atmosphere between 12 to 15 kilometres. It is associated with some of the strongest winds on Earth, reaching over 280 miles per hour at times. As this jet sits between the descending branches of the Hadley and Ferrel cells, there is little associated weather. The polar front jet forms in a different way. This jet sits between the rising branches of the polar and Ferrel cells. It marks the boundary between cold polar air and warm tropical air, known as the polar front. The polar front jet occurs at a height of 11 to 13 kilometres and is primarily the result of the temperature contrast across the polar front. The stronger the temperature contrast across the front, the stronger the jet. So it follows that the polar front jet is stronger in the winter than the summer. Waves or ripples along the jet stream can cause Atlantic depressions to deepen explosively as they are steered towards the UK. Winds at the surface are also subject to deflection from the Coriolis force. The surface flow of the Hadley cells form the persistent trade winds. As air flows towards the equator, it is deflected towards the west in both hemispheres, forming the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. The persistence of these winds allowed sailing ships to cross the Atlantic and opened up trade routes between Europe and America, giving them their name. The surface wind in the Ferrel cells would flow from a southerly direction in the northern hemisphere, but the Coriolis effect causes this wind to be deflected to the right, leading to the prevailing westerly and southwesterly winds often experienced over the UK. This setup is not unique to our planet. Jupiter also has circulation cells similar to those on Earth. A day on Jupiter lasts for about 9.5 hours, so it is rotating much more quickly than the Earth. The great size and fast rotation of this planet makes the Coriolis effect very strong. This splits the Jovian atmosphere into many circulation cells in each hemisphere, producing numerous alternating bands of rising and falling air and giving Jupiter a distinctly striped appearance.
The illustration on this slide shows the different air circulation cells described in the previous videos. The Earth's atmosphere is made up of different layers. The lowest layer is the troposphere, which can range from 20,000 feet at the poles to nearly 60,000 feet at the equator. 75% of the atmospheric mass is contained in the troposphere, so the upper layers have very little density. Most of the Earth's weather occurs in the troposphere, where temperatures decrease as altitude increases. This characteristic allows warm air to rise. When a parcel of warm air containing water vapor rises, it will eventually cool to the dew point and the water will condense to form clouds and precipitation. The tropopause forms the upper boundary of the troposphere. Here temperatures become stable and no longer decrease with increasing altitude. In the stratosphere, temperatures increase with altitude. Air masses with different density, humidity, and temperature characteristics constantly move across the Earth's surface. The boundary between these air masses is called a front. A cold front occurs when a mass of cold air advances into an area of warmer air. The cold air is more dense and pushes the warmer air up higher into the atmosphere, causing clouds and precipitation. A warm front occurs when warm air advances into colder air, causing the warmer air to ride over the top of the cold air mass. As the warm air rises, the moisture it contains will condense out in the form of clouds and precipitation. Pilots flying toward an advancing warm front will often experience cloud ceilings that become lower and lower as the aircraft gets closer to the frontal boundary. Water moves from a liquid to a vapor state, and back again, through a continuous cycle of evaporation and condensation. The clouds that form from water condensing in the atmosphere are classified according to their height and their characteristics. There are high, middle, and low clouds, as well as clouds with vertical development. Stratus clouds resemble a large blanket and are associated with stable air. Cumulus clouds resemble puffy cotton balls and are associated with turbulent air caused by updrafts. The prefix nimbo is added when either of these cloud types produces rain. Lenticular clouds resemble a concave lens. They often occur when strong winds pass over mountainous regions, and are associated with severe turbulence. Thunderstorms occur when moist, unstable air is lifted by surface heating, or is pushed upward by rising terrain or a front. They are extremely dangerous to aircraft and should be given a wide berth, at least 20 miles. Thunderstorms typically have a short lifespan and usually move through their three stages of development: the towering cumulus stage, the mature stage, and the dissipating stage, in less than an hour. The three slides that follow show these stages. Afterwards, a time-lapse video shows a developing thunderstorm. Inside a thunderstorm, there are strong updrafts and downdrafts that can potentially break apart an aircraft. If a pilot accidentally enters a thunderstorm, such as when flying at night, it is best to keep flying straight ahead and to keep a level attitude, rather than attempting to maintain altitude. Trying to turn around will only increase the time spent inside the cell and subject the aircraft to greater G loads from making the turn. Fog is simply a low cloud that has its base within 50 feet of the ground. Radiation fog typically occurs on clear, calm, humid nights over low-lying flat surfaces. As the ground radiates away heat, the adjacent air is cooled to its dew point. Advection fog occurs when moist air moves over a cold surface. The air is cooled from below until it reaches the dew point and becomes fully saturated and condenses. Upslope fog occurs when moist, stable air is pushed up sloping terrain by the wind. As the air cools, it becomes saturated and condensation occurs. Icing poses a risk to aircraft when flying through visible moisture at temperatures near freezing. It increases drag, adds weight, reduces lift, and increases the stall speed. Aircraft icing is classified into several types: clear, rime, and mixed. Clear ice is transparent and can extend back from the leading edge to coat portions of the wing surface. Rime ice primarily forms at the leading edge and is milky white in appearance. Mixed icing is a combination of clear and rime ice. Freezing rain has the highest accumulation rate and is the most hazardous form of aircraft icing. Freezing rain can completely coat a wing surface in a short time, degrading its aerodynamic properties. Icing occurs when the temperature is below freezing and there is visible moisture, so it can be avoided by staying out of the clouds. If you inadvertently fly into icing conditions, the best escape is usually a 180-degree turn back to non-icing conditions. If this is not possible, an attempt can be made to fly above the clouds or descend to warmer temperatures. Pilots should never take off when there is frost on the aircraft. Although it appears relatively benign, it can reduce lift by 30% and increase drag by 40%. The following video shows a news report on an airplane crash that occurred when the pilot departed with frost on the wings.
4 men who were taking off from an airstrip east of Mount Hamilton. Judy Garcia explains what happened.
Greg Cullen was one of 4 people on board the Cessna 210 when it began to take off just before 8 in the morning.
We were taking off from the runway, and we got up. We were about 100 or 200 feet in the air, and the plane, it was though it lost power, although I don't think anything happened with the engine, and we just started heading towards the ground, and we crashed and hit the ground, and thank God above we were all alive. Everyone was screaming and yelling and trying to get out of the plane as fast as possible, but the doors were jammed shut, and we finally got out and realized that we were all okay. At least none of us was dead.
All 4 were taken to San Jose Medical Center for treatment. The accident happened at the Isabel Valley Ranch, just east of Mount Hamilton.
It's a private airstrip here on the ranch used by the people that own the property here.
The plane didn't, it just hit the ground and kept going forward. It didn't tumble, thankfully. Otherwise, I think we'd have been in much worse shape.
According to the sheriff's department, the men had just flown into the ranch the day before for a business meeting. Judy Garcia, KNTV News.
One of the passengers, Lucas Stamos, will remain in the hospital for treatment of compression fractures to his spine. The other 3 men, including the pilot Donald Huntley, were treated and released. Developer Barry Swenson suffered cuts and bruises.
Weapon, and that is certainly an
Swenson is one of 4 men who were taking off from an airstrip east of Mount Hamilton. Judy Garcia explains what happened.
Greg Cullen was one of 4 people on board the Cessna 210 when it began to take off just before 8 in the morning.
We were taking off from the runway, and we got up. We were about 100 or 200 feet in the air, and the plane, it was though it lost power, although I don't think anything happened with the engine, and we just started heading towards the ground, and we crashed and hit the ground, and thank God above we were all alive. Everyone was screaming and yelling and trying to get out of the plane as fast as possible, but the doors were jammed shut, and we finally got out and realized that we were all okay. At least none of us was dead.
All 4 were taken to San Jose Medical Center for treatment. The accident happened at the Isabel Valley Ranch, just east of Mount Hamilton.
It's a private airstrip here on the ranch used by the people that own the property here.
The plane didn't, it just hit the ground and kept going forward. It didn't tumble, thankfully. Otherwise, I think we would have been much worse shape.
According to the sheriff's department, the men had just flown into the ranch the day before for a business meeting. Judy Garcia, KNTV News.
One of the passengers, Lucas Stamos, will remain in the hospital for treatment of compression fractures to his spine. The other 3 men, including the pilot Donald Huntley, were treated and released. Developer Barry Swenson is one of 4 men who were taking off from an airstrip east of Mount Hamilton. Judy Garcia explains what happened.
Greg Cullen was one of 4 people on board the Cessna 210 when it began to take off just before 8 in the morning.
We were taking off from the runway, and we got up. We were about 100 or 200 feet in the air, and the plane, it was though it lost power, although I don't think anything happened with the engine. And we just started heading towards the ground, and we crashed and hit the ground, and thank God above we were all alive. Everyone was screaming and yelling and trying to get out of the plane as fast as possible, but the doors were jammed shut, and we finally got out and realized that we were all okay. At least none of us was dead.
All 4 were taken to San Jose Medical Center for treatment. The accident happened at the Isabel Valley Ranch, just east of Mount Hamilton.
It's a private airstrip here on the ranch used by the people that own the property here.
The plane didn't, it just hit the ground and kept going forward. It didn't tumble, thankfully. Otherwise, I think we would have been much worse shape.
According to the sheriff's department, the men had just flown into the ranch the day before for a business meeting. Judy Garcia, KNTV News.
One of the passengers, Lucas Stamos, will remain in the hospital for treatment of compression fractures to his spine. The other 3 men, including the pilot Donald Huntley, were treated and released. Developer Barry Swenson suffered cuts and bruises.
Four common causes of low-level wind shear are frontal activity, thunderstorms, temperature inversions, and surface obstructions. The sample FAA test questions that follow will help you prepare for the questions on weather in the private pilot written exam.